All right, ladies and gentlemen, we're going to do Lewis structures, and then we're going to redraw the Lewis structure with the correct geometry, and then we're going to use the redrawn molecule with the correct geometry to put dipole vectors on the molecule. We don't know what that means. Some of us might. And then we're going to figure out the net polarity of the molecule. And we know why polarity is important. We did a relevance of organic chemistry feature on that. All right, here we go. First one's somewhat inorganic. So just to be safe, we'll count the valence electrons on that one. The second one looks pretty inorganic too. Doesn't have H on C, although it's organic. There you go. Go figure. Valence electrons. 7 for fluorine. How did I know that? It's in the halogen column with a Roman numeral VII above it. And then 5 for nitrogen. 1 each for the hydrogens, and there's 3 of them. Now, if you have a cation charge, are you missing a valence electron, or do you have an extra valence electron? You're missing one. So 12 plus 3 is 15, minus 1 is 14. Skeleton. What goes in the middle? F only makes 1 bond, everybody, so don't put F in the middle ever. If it's got 1 bond, it has to be sticking on the outside, so it can stick at the middle. And the N makes multiple bonds. H doesn't make multiple bonds. There's 3 H's too. All right, I'm going to put the N in the middle. I'm going to stick the F. Hello? I don't know what happened. I'm going to stick the F on top. And I'm going to space things out. This is not normal nitrogen, is it? Are you freaking out? You knew it wasn't going to be neutral. How come? It's got a charge. Yeah, nitrogen, when it's neutral, has that behavior of 3 bonds in 1 lone pair. Remember, that table we constructed was for neutral atoms. Looked at it from last time. Let's see. Oh, that's what he meant by neutral atoms, right? Okay, now, if you have a 4th bond in nitrogen, doesn't that give it a plus charge? Think about it. It's sharing 8 electrons right there. That's like owning 4. Nitrogen on the periodic table owns 5. I don't know if any of that got on the video, but nitrogen on the periodic table owns 5. This nitrogen is sharing 8, which is like owning 4. That's 4. It's got 1 less than the periodic table. It's a cationic formal charge. And because we do it that way in this course, we don't need the square parentheses with the plus outside. I know this has a +1. Look at it. In fact, I know more than that. I know where the plus it lives, right? That's the danger of the square brackets with the charge. You don't know where that charge really resides if you do it that way, right? But you weren't ready for that then. That was 141. You weren't ready yet. You're ready now. And that's A and B. No, that's just A. That is not the proper geometry for a central atom having 4 bonds. It isn't. I'm starting to stress out, I know, because you learned all those geometries in 141 and all those angles. And you're saying, do we have to do that again? Well, you do, but there's a lot less angles and a lot less geometry in this course. Okay. It has everything to do with hybridization. Okay. Hybridization. We can't use atomic orbitals to make bonds because then we wouldn't have evenly spaced atoms around a central atom. And we all know that atoms obey the valence shell electron pair repulsion theory because electrons hate each other. That's a great theory name, right? It says what it is. Valence shell electron pairs repel each other, the separ. And we got to figure out how many groups of atoms we're getting away from each other. I have to tell you how to do that. You need to know how to do it on every test from now on. There's only two things you need to count for a central atom to figure out its geometry. The number of sigma bonds and the number of lone pairs. Those will tell you how many sets of atoms, sets of electrons you need to get away from each other. Only sigma bonds and lone pairs. Remember, every atom, when it's bonded to another atom, has exactly one sigma bond. Do not rewrite that sentence in any way, shape, or form. Any two atoms that are bonded to each other have exactly one sigma bond. Okay, if there's more than one bond between the two atoms, what are the other types of bonds called? We're supposed to know already. Pi. Did I tell you to count pi? No, there's a reason. If there's a sigma bond between two atoms, the pi has to be above and below those two atoms. You can't get the pi away from the sigma. If you've drawn the sigma, then the pi has to be right above and below that. You can't use the space where the sigma was, that space is taken. You have to use a new space that's almost as close. And that's called pi. Okay? So, I'm going to keep bothering you. This nitrogen, how many sigma bonds? 4. How many lone pairs on that nitrogen? Not a normal nitrogen, is it? There are none. So 4 plus 0, how many fingers you got in the air? 4. That's how you do hybridization. You ready? S, P, P, P. Group the P's. How many were there? 3. It's called Sp3 hybridization. Nice. 4 sigma plus 0 lone pairs equals 4. Equals Sp3. Sp3 angle, always the same in this class. You remember from back in the day? Maybe not. We have 3 angles to learn. This is the smallest one, 109.5 degrees. Okay? So if I'm going to draw the Lewis structure with the right geometry, oh, I didn't finish my Lewis structure. What's the nature of fluorine? This is part A. We didn't quite finish. Fluorine has not got an octet. What do I have to put on fluorine? 3 lone pairs. If you're having trouble with the nature of atoms, please look at the periodic table. Remember carbon, 4, no lone pairs. Always start there. Next one over, 1 less bond, 1 more lone pair. Nitrogen, 1 less bond, it's right beside carbon, 1 less bond, 1 more lone pair, 3 and 1. Go to oxygen, 1 less bond again, 1 more lone pair again, 2 and 2. Go to fluorine, 1 less bond, you're down to 1. 1 more lone pair, you're up to 3. So those 4 you got to be rock solid on, like yesterday you did the answer. Okay? Okay, so 3 lone pairs there, right? And now for proper geometry. I'm going to draw the F straight up again. And I can't draw the H at 90 degrees like I did before. 109.5 is a little more, right? How about that? That's more than 90, right? Now the problem is next, the other 2 bonds are not in the plane of the page. A tetrahedron is 3-dimensional with even spacing around it. I have one right here. It's not the same molecule, but I can make it similar. Oh, why not? We can make fluorine be green and H is white. I've drawn, oops, I drew this. F straight up, H here. This H is sticking at you and downwards, right? It's below horizontal, and it's sticking at you and downwards, this H right here. Look. This here, sticking at you, and a little bit down, and a little to your right. Sadly, on the screen, it's a little to my left. So, sticking straight at you, a little bit down, is an H. And the one I'm holding right now, if you're looking head on, isn't the one I'm holding now right behind this one that I just drew with the wedge? So it's right in behind it. Does that mean the angle's small? No, it's the same angle, right? They're all the same angle. So here's how you draw it. It's right in behind the other H. Look at that. You drew your first tetrahedron, maybe. I don't know. Maybe you drew one before. And this part B didn't ask for a Lewis structure, right? Just the right geometry. So unless you're asked for a Lewis structure, you don't have to draw all the lone pairs. You can stop drawing lone pairs for part B. But I do need to see a tetrahedron, don't I? And I always want to see the formal charge. Don't skip formal charges ever. Every error of a formal charge on every exam in this course costs you a half point. Every time it happens. If you're doing the same error over and over in the same question, yes, you will be docked a half point each time. Yeah. That's the only time I dock for the same mistake over and over, because we have to kill that mistake. We have to make it a thing of the past. That kind of error is terrible. Cations are nothing like neutral molecules or neutral atoms. Okay, did we do all the parts? No. Redraw the structure with proper geometry, correct. Dipole vectors, we don't know how to do those. But if I told you a dipole vector just indicates how polar a bond is, and it's based strictly on electronegativity, and some of you have read a little bit, right? You saw the table of electronegativities you must learn. Did you see it once or twice? The same table appears twice in chapter 1 with the same big bold letters saying you must learn this, right? I liken it to, if you don't learn those, it would be like trying to read a book without knowing the definition of the word the, and you'd have to look up the word the every time you saw it in a book. Would you ever finish this book? No, we can't get, we need to be able to talk about chemistry, and we can't without electronegativity. Fundamental electricity and electronegativity. And they're not, it's not a lot of numbers, and there are memory tricks given in the textbook and on at least 3 or 4 videos. I just keep re-saying the same thing. Things like Hewlett-Packard. For some reason, I grouped those two together. And pH meter. Why am I grouping those together? Because those atoms have the same electronegativity. You're going to learn them on your own. You're going to find your way. The only electronegativities I need for this page are F. These are electronegativities. I call that EN. EN. F is 4.0. Carbon is 2.5. I saw hydrogen here. 2.1. I was going to say 1.2. Listexia. 2.1. And I think we have an N right here. N right beside carbon, 3.0. We need those for discussion. So let's do the F bonded to the C. F bonded to N. Sorry, there's no F bonded to C. F bonded to N, what's the difference between the two numbers? Equals 4.0 minus 3.0, 1.0. I'm going to put a dipole on the bond, and I'm going to draw it about that tall. Yeah. And it should follow the exact direction of the bond. That's not. It's between resolution points. There, that is. And a vector always points away from the less electronegative atom towards the more electronegative atom. Which of the atoms, F or N, is more positive in that bond? Or put it another way, because F pulls the electrons more strongly, that's what the 4 means, right? F is slightly negative. So what does nitrogen feel a bit like? Slightly positive. Does that not look like a plus sign near the nitrogen? Doesn't it? Where do you put the plus part of the vector? Less electronegative atom. Where do you put the arrowhead? More electronegative atom. There you go. So NH, we're going to point towards N, correct? And the arrows will be smaller. Do you know how I know that? Delta En for N bonded to H is 3.0 minus 2.1. They're not much smaller, but they're a teeny bit smaller, 10% smaller, right? So I'll do those in black, just a little shorter than the first one. This one's a wedge. Wedges are misleading because they have 3D. Really, I'll show you. We got the NH, I don't know, which way is it pointing to? Is that way or? It is that way, right? And the other NH, the wedge, is sticking that way. Now, if you're looking head on at an object that's coming at you, it looks like the bond is shorter. It's what do you call it? A visual trick? I don't know. It looks shorter than it is because you're only really seeing here to here, and it's 3D. That's why it doesn't look the same length. And then the same for this one. Okay. And then we have to add those up. Ooh. We have to add those dipoles. Adding dipoles is easy. Dipole vectors, they're called. Vectors have direction and magnitude. How long the arrow is the magnitude, and which way it's pointing is obviously the direction. Just copy any one of those vectors in the same direction you see it. I'm going to copy that black one to the right. I just picked it. And where it ends is where the next one begins. You pick one. I'm going to pick the red one. Why not? Then we'll move them closer to my molecule. So the black one, did they do a good cop? Not a bad job copying it. They're supposed to be identical. I'm not a good artist. You know that already. Red one, I did, for me, that's remarkable. Okay. All right. Then this is going to be where the other one ended. Remember, I went number one. The very beginning was here. Very beginning. Double N? Yeah. Maybe. I don't know. We're not finished. We're going to go dash. And then wedge. Wow. Straight up. Wedge. Right? Up. And then, yeah. The wedge. I must want to copy paste it. I got extra, I know. That almost ends where it started, didn't it? I don't like it. I don't like it. I'm gonna go with it though. Z. And Z. There. So the net, this is the very end right here. If I was a better artist, it would be a straight up and down. I'm not a good artist. Very end. And the net, I shouldn't choose red. It's purple. Very start to very end. Net dipole. Slightly polar. It's so small that this molecule is not very polar, is what I'm trying to say. That's a very small arrow, right? There's a better way to do it. Oh, and I will give you the same comfort I gave the morning section. Because right now you're saying, I can't do that. I don't make you do this on the test at all. I could ask you to just estimate the overall net dipole. That I will verbally go through right now to show you why it should be slightly off. Okay? And before I do that, I just want to talk about the wedge and the dash, because that's what messes with my brain. I don't have a 3D brain. But we have a question first. That's another problem with this question. I drew all of the NH dipoles wrong. I should be fired. It's okay. We caught it in time. See? I need your help so I don't get fired. Yeah, I went to all that length to tell you the dipole goes from the less electronegative atom towards the more electronegative atom, and then I contradicted myself immediately. You know, it makes me want to scrap the video. But, you know, mistakes are also educational. Every one of those black arrows is written the wrong direction, right? And maybe the artwork's going to work out a little better in this when we're done. All right. Quickest way? Who knows? We point from the H towards the N, right? Okay. So definitely get skinny, but there's your arrow, and there's the plus sign, and here's the arrow. There's the plus sign, and here's the arrow and the plus sign, and that's not 90% the red one anymore. I'm gonna redraw that because it needs to be 90% as long as the red one. Do you remember why? Why is this arrow 90% the length of the one above it? Down here, 90%, 100%. And now I'll start with the same black arrow that I just drew. Then the red arrow goes straight up. Oh, I'll do all the blacks first. How's that? Why not? We got this one. That's not black. There was a black, and there's a black. Yeah. Did I copy it pretty well? Not bad. I've done better. And then this one's going to the right. And then the red. Let me copy it better. Let me get better. Control Z, 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 Z. Right where that one is. There you go. Now it's messy, but the very start was here, and the very end is here. Start, very start. The very beginning, very end. And the net dipole is large. It should go all the way from very start to very end. And it'll be a straight line, very start to very end. You like it? And it's a dipole. Start has the plus, the end has the minus. Net dipole. And this thing is a very polar molecule. That should have been another clue I was doing things wrong. Because it is a polar molecule. A lot more polar than the net before. Look at the net before. That was for this guy here, A and B. Oh, no. That was the wrong net dipole. That's what I'm talking about. Okay. Bit of a messy video. I'm going to talk to you about how we can more easily get to the net without doing all this work. Wedges and dashes, big problem. So I know it's the opposite direction of the way I drew these, but I think it works better for me to be a teacher looking at you this direction. Here's a wedge, here's a dash, right? Now pretend they're both, let's not even use that example anymore. Pretend they're pointing away like my fingers are pointing, okay? If I add those two together, I guarantee the end of the addition will be right in front of my eyes, in the plane of the page. Remember, my body's in the plane of the page. There's the wedge out of the page. There's the dash behind the page. Two equal vectors doing that. They're going to go out there and then add that one, and it comes back to the same line as the plane, right? So that's the way you should do wedge dash. Do those two first. When you're adding numbers, like 4 numbers, do you have to do them in any particular order? No. Vectors, same story. I'm just going to add these 2 black ones over here, and I hope you agree when I add just those 2, they point towards the end. I'm going to call this one A, and this one B, and then A plus B, no surprise, is right between them in the plane of the page. Right there. I got a dead spot on my screen. Okay. Right between them. And now it's easier to see that that one goes to the right as much as this one goes to the left. This one, they go up about the same, right? So if you add A plus B to C, then you got something straight up. And then the red one is just straight up some more, right? Quite a bit more. So you're definitely seeing the straight up now, right? You're going to do A plus B, and then add C, and then that would be A plus B plus C would be just straight up. And then the red, add that to the top, and you're going to get the purple, aren't you? Okay? Put the red on top of that. That would be A plus C plus D, and you'd get the purple. The red right here on top would go and make about this. You good? And I already promised we're not going to be doing this question on the test. That's when you started zoning out. I know. All right. But it's important to be able to see that how polarity is determined. Visualize. It's all based on geometry and bonding, isn't it? And electronegativity. And keep your activity, and we'll do the next one on the next page.